So far we have seen basic Turing machine, right? Now we are going to see variations of Turing machine. That means we are going to modify the structure of your Turing machine little bit, and we are going to, have variations. But fortunately, the expressive power is same. That means if a language is accepted by basic Turing machine, then that language will be definitely accepted by your variations, and any language is accepted by this variation is also accepted by your basic Turing machine. That means, so with respect to acceptance power, your basic Turing machine is equivalent to all these variations. We will see that variations one by one. So one is multi-track Turing machine, second one multi-tape Turing machine, after that two-stack machine, counter machine, in that we have two counter, four counter, then non-deterministic Turing machine. We will see one by one and we try to understand the definitions of that variations. Let us begin with multi-track Turing machine. So first of all, we take a basic Turing machine. This is your basic Turing machine, correct? So you have semi-infinite tape. This is left-hand marker. Now these are all various cells, correct? Now you have a finite control. Let's call C, and there is a read and write head. Currently it is, let's say, pointing here, and this is the configuration at this moment. That means after some point of time, after running for some time, so this is your Turing machine's configuration. That means these are all tape symbols A, B, C, A, B something, and currently your control is pointing here, and this is the configuration of your tape. Okay, these are all, let's say, blanks. Now let's call it as a machine Raju. Okay, the name of the machine is Raju, which is basic Turing machine. Now I'm going to show you multi-track Turing machine. In multi-track Turing machine, exactly everything is same. The only variation comes here with respect to the semi-infinite tape. So here also it is a semi-infinite tape, but you will have multiple tracks like this. The tape is logically or physically, whatever, it is divided into multiple tracks. So see, track number 1, track number 1, track number 2, track number 3, in that way. So one of the example configuration will be like this. Maybe A, B, some blank, B, C, some blank, in that way. Okay. So at this moment, this is your configuration, whatever it is. Now here also you will have finite control, and that head is pointing currently here. Here also you will have only one head. That means you are going to point to only one, I can say, cell. But of course that cell is, we have three cells here, but I can say we can point to only one column. We don't have three pointers to point one here, one here, one here, like that. Okay. So now how this machine is going to work, I will tell you. So whenever you see a symbol, here we are seeing multiple symbols. That's it. Here you see only one symbol, correct, at a time. That is the difference. Example, whenever you are in a state called Q, and whenever you see a symbol here, you see three symbols. Currently we are seeing B comma C comma empty. That means B comma C comma blank. After seeing these three symbols, then we are going to move to a state called, let's say, Q next, and that Q next is an arbitrary state. Then we will be modifying all these symbols, if and all, if you want. Let's modify them. B is going to be something X, C is going to be Y, and that blank is going to be Z. That is the way. So I want to change. So this is the typical transition function or transition in this multi-track Turing machine. Now let me show picture really. What are you doing is, whenever you are in a state Q, by seeing the three symbols, then we are going to modify them. Okay, if we want. Otherwise we keep them as it is, like basic Turing machine. Okay, X, Y and Z. After that you have to go left or right. That means we have to add one more step. What is that? Right or left. When you say right, what is going to happen is your control is going to be moved to next position. That means we come here. It is exactly same as your basic Turing machine, but here you are seeing three symbols and you are modifying three symbols, and remaining everything is same. Okay. Now if that is the case, now the question, let's call it as Rani. Now Rani claims like this: my dear Raju, you are poor. After all, you have semi-infinite tape with only one track. See, I have three tracks. That means I am 3 times powerful than you. So that is absolutely wrong, because we are going to prove that Raju and Rani are equivalent. How you see? Definitely it looks like, because we have 3 tracks, by using only one track and by keeping these tracks, remaining 2 tracks empty without touching them, if you only use first track, then at least we can do like Raju, correct? That means Raju's functionality can be achieved. That means So initially my guess is this multi-track Turing machine is either equivalent to this single track Turing machine or maybe more powerful than that, isn't it? But unfortunately, otherwise, fortunately I can say Raju and Rani are equivalent. That means these two machines are having same equivalence power. Let's see that. Okay. Now we'll see why this Rani and Raju are equivalent. Okay. So Raju is going to say like this, my dear Rani, of course you are seeing two symbols, right? Now I am going to see only one symbol, but still I can achieve exactly what you can achieve. How you see? Rather than symbols ABC which you are taking, I modify my input symbols. So here input symbols will be having a structure. So they are not like ABC, they will be having two component thing like this AB. From now onwards, the input symbols and tape symbols, let me show the tape symbols. The tape symbols in Raju's machine will be AB, AC, BC like this. They are not like ABC. So Rani is using ABC. Whenever Rani uses ABC, I use AB, AC, BC, in that way all combinations, okay, AA, BB, every possibility, okay. Now this will be the tape alphabet. Using that, Raju can achieve exactly what Rani is achieving. Example, we will see. Rani, at this moment, what are you doing? You see, you have left hand marker, I have a left hand marker. You have A comma B in first track. I mean, first track you have A, second track you have B, right? But I have only one track, but I have a combination AB. For me, AB is a unbreakable symbol. It's a symbol. Don't touch that. Similarly, I have AC kind of symbols. I don't have like A comma B, but still I can achieve exactly what you are achieving. So you are feeling like you have two tracks, but the same thing I am going to achieve using only one track. We will see that. AB, AC, BC, you have blank, 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 right? Here also AB, AC, BC, blank, blank. Initially, let's say both are having same configuration. Now how equally they are going to move, we will see. We'll ask Rani. Rani, so what is your code? How you are going to move your things? Rani says like this. At any time after seeing the input like A comma C, maybe I do like this. I go right side, but before going to the right side, I make this as C, this as C. Okay. Then how you achieve the same thing? Very simple. So Raju is going to do like this. He is seeing only one symbol, right? So whenever he has a symbol AC, now he will be like this. Example, so the state was Q, okay, some Q. By seeing AC symbol, what he will do is, he will go to exactly the state which Rani is going. He is a copycat. Raju is a copycat. Whatever Rani does, same thing Raju is going to do, you see. So if Rani goes to right side, Raju is also going to right side. If Rani sees, A comma C symbols together, okay, Raju is seeing AC combination symbol, okay, almost same, right? Now, he will design his system like this. So on AC, what he will do is, what Rani is doing, she modified two symbols, A to C, C to C. Then he will modify only one symbol called AC to CC symbol. Now you see, if he does that, what is going to happen? Then AC symbol will be modified to CC symbol. Then exactly same configuration we are achieving. Now Rani went right side. We also will go right side. We have a provision for that. So what is the difference you are seeing? Correct. So both are having same configuration after each and every step. So that's why finally Raju says that, Rani, whatever you do, I can simulate the same thing with my machine. You take A, B kind of symbols for you. These are the symbols, but I take combination symbols A, B, C, C. Symbols are different, but the concept is same. Whatever you accept, even I can accept. In that way, so Raju's machine and Rani's machine are equivalent with respect to power. In that way, Raju can simulate Rani. Understand? So in that way we can say that Raju and Rani are equivalent. So multi-track machine, which is nothing but Rani, is nothing but equivalent to single track Turing machine. Remember it. Now we'll go to multi-tape Turing machine. Let me define what is multi-tape Turing machine. Okay. In multi-tape Turing machine, you will be having multiple tapes this time. Okay. So you have tape 1, tape 2. Let me take another tape, tape 3. So you have multiple tapes. Everything is a semi-infinite tape. This is left hand marker. Okay. Now it looks like we have lot of power. We will see what happens. You have some configuration like this: A, B, A. So B something A, something C. Initially it is like loaded like this. Okay. Something blank symbol, blank symbol, blank symbol. Okay. Now So infinite tapes. You have three controls now in multi-tape Turing machine. So there will be three controls. One control is pointing to tape 1, second control is pointing to another tape anywhere, third control is pointing somewhere here, let's say that way. Okay, for easy understanding, so what I do is I show like this. Let's say your third control is pointing to this one. So here you have three controls now, right? That means three heads, not three controls, only one control but three heads. Okay, that is multi-tape Turing machine. So each read and write head is going to point to one of the tape and a different position. We don't know. It is not compulsory that every pointer should point to same position. It's not compulsory. Okay, such machine is called multi-tape Turing machine. Now you have everything same. What is that? You have sigma input alphabet, tape alphabet, everything you will have. So like you will be having reject state, final state and start state. Now what is the transition function? Remember one thing, transition function is heart of everything. Okay, that is a functionality. Remaining things you can easily understand. We'll see what is the transition function of this multi-tape Turing machine. It will be like this. Initially you will be in some state, let's say Q. On that Q we will be seeing all the inputs. Tape number 1's input is what? A, because first head is pointing to this one, right? So we see A, and because of this pointer we see blank symbol, and because of this pointer we will see C. By seeing these three we are going to take a decision. We are going to move to another state, that is, let's say Q next. Sir, basic Turing machine also does same. Q, we will go from one state to another state. Yes, it is same. But here you are seeing three symbols. Sir, in multi-track Turing machine also we have seen three symbols. Yes. What is the difference between multi-track and this one? Here you have multiple heads. Okay. Each and every head is pointing to a different cell. But where in multi-track there is only one head, it was pointing to a particular column. Right. Here, see. One pointer here, one pointer here, one pointer here. It looks like, it is having more power than your multi-track Turing machine. We will see that whether it is correct or not. Now Q next, and anything else. So here you have A. After seeing A, you can modify it. Let's say we are modifying it to X. We want to modify this blank to Y, and we want to modify this C to Z. Then it will be X comma Y comma Z. That is the way this transition function is defined. Apart from that, we have to do one thing. We have to move the heads, right? Generally, if you have only head 1, we move either left or right. But here, there are three heads. We have to move them independently. That is the power of this multi-tape Turing machine. So that's why one pointer can go to left, another pointer can go to right, another pointer can go to left. So these three can independently move. That is what I would like to tell. So this is about multi-tape Turing machine's definition. Now, is it equivalent to your basic Turing machine? Otherwise it is powerful than your basic Turing machine. We have to see. We will see that. For that we try to compare this multi-tape Turing machine with multi-track Turing machine, because these two are quite similar, right? So that's why I am going to compare multi-track Turing machine versus multi-tape. Sir, why don't you take basic? Because it is easy to compare. If these two are equivalent, already multi-track is equivalent to basic Turing machine, then automatically these three will become equivalent. Now I am going to prove that multi-track Turing machine is equivalent to multi-tape Turing machine. Okay, yeah, let's do that. Now we'll prove that multi-tape Turing machine is equivalent to multi-track Turing machine. Why? We will see that. So let's represent multi-tape Turing machine as Rahim, and we have Sultana, which is representing this multi-track Turing machine. So Sultana has only one head, right? One tape head. Currently it is pointing, let's say, somewhere here. Initial, always Sultana's head points here. Okay. Now Rahim's heads, there are two heads. One is pointing to one tape, one is pointing to another tape. So now let's see the conversation between these two. Rahim says like this: my dear Sultana, I am better than you. Then Sultana says, no, I am equivalent to you. Rahim says that let's start comparison. I have two infinite tapes. How many you have? Then Sultana says that it doesn't matter. When I have one infinite tape I have multiple tracks, right? Then somehow I can simulate you. Then Rahim says that it is impossible because I have two heads, you see, one is pointing to one is pointing to one. Maybe I can have a better behavior than you. Then Sultana says that don't worry, if you have multiple heads, then one by one I will simulate. We will see how it is possible at this moment. So Sultana says that, my dear Rahim, see, you have AB blank blank something here, AB BA blank blank, right? Approximately I also have, you see, AA in my first in the first cell, AA BB I have a cap. I will tell you why I kept cap. AB BA exactly, we have same configuration almost. That means Sultana saying that, Rahim, I simply simulate you, whatever you do I do. If I do that, will you agree that I am equivalent to you? Then Rahim says that, yes, I will agree that when whatever I do, if you can do, then I agree. Then he says like that. We will see that whether Sultana can simulate Rahim or not. That means finally here what we are going to do is, whatever Rahim does, Sultana is going to do. Let's see whether it is possible or not. For that, Sultana is going to have extra code plus Rahim's code. Since why Rahim's code? Because we are going to do copy. Whatever Rahim does, we are going to do, because we are going to prove that whatever Rahim achieves, we also should achieve. That's why we are going to copy Rahim's code. Let's do that. First of all, we'll ask Rahim. Initially, now we are same Rahim. Sultana is saying like that, my dear Rahim, at this moment we are having same configuration, right? Like whatever you are accepting, I am accepting. Now what are you going to do extra? Now Rahim says that, see, now I am in Q state. On input something, now I am seeing two inputs, one is B, second one is B. So Q on B, I will go like this. I will go to a state Q next. Okay, now I will make B to something C, otherwise let's take B to A. B to A, this B to, let's say, something B. Let me otherwise assume that it is C. A comma C, and one left, one right. So finally Rahim says that, see, from Q I went to Q next. Can you go like that? Sultana says that, yes, I can go like that. Now I am changing B to A and another B to C, and I am changing one tape to left, one tape to right. First of all, we'll see what Rahim is going to achieve. So Rahim is going to achieve like this. B will become A, correct? Yeah, this B will become C. After that, he moved one pointer to left, first pointer to left, second pointer to right. That means first pointer to left, second pointer to right. Right means like this. Then he will challenge Sultana. Sultana, can you achieve the same with your Turing machine? Then Sultana says that, yes, I can achieve by extra code. I am going to have a very lengthy code, but using that, whatever you have, I can achieve. You see what? Before that, she will tell like this. You know one thing, why these markers, these symbols? So Sultana says like that. See, Mr. Rahim, I am using especially this cap symbol to represent that your first head is pointing here. Yes or no? You see, it was pointing here, correct? That's why I used a special symbol to remember that. That means whatever you are doing, I am remembering. Since you have two tape symbols, right? Two tapes, and sorry, you have two tape pointers, right? I have only one pointer. That's why I am going to use this tape alphabets. With that, I am going to remember the positions. See, you had a pointer here initially. That's why I used this symbol B with cap. So that now what I do is, I do like this. I have extra code. That extra code is going to do like this. My dear Rahim, listen. First of all, I'll search for this marker. Okay. Now, after coming to this marker, now I will go to your state first. I'll ask your state. Mr. Rahim, on B, what you did? You changed that to A, right? Then I change it to A. Fine. After that, what about that pointer movement? You will move it left, right? Then I also move this symbol to here. So I have extra code. Okay, it's not a one step, but I take some 10-15 steps and I achieve it. What finally your Sultana is doing? Using the extra code. First she is scanning this tape, and she is finding this cap symbol. Whenever there is a cap symbol, so that input will be modified to exactly like A, and after that what she is doing is she is moving the cap pointer to, that means cap symbol, to next input. such a way this extra code will work. Okay, we can design it, because you know that Turing machine can be designed such a way that we can scan the entire tape, right? And one more thing, we can scan any number of times. That's why, so this extra code definitely can achieve it. After that, she will not stop. Rahim says that, Sultana, are you done? Then Sultana says, no. Still, my code will work such a way that, so it will scan. So my control will come like this. That means my head will come back. For that I have a code. Then after that again it will come like this. This time it will see a symbol such a way that in the second track there is a cap. I will stop. Then I will see the symbol B. Now I will go to exactly like your state. I remember your state. Then Rahim asks, how do you know that on Q, on B, I am moving it, I am changing it to C. How do you know that? My dear stupid Rahim, I have your entire code. Whatever you do, I can do, because I simply copy your code. Okay, that means that's why we have a Rahim's code also. So in the Rahim's code, Q on B, this C, Q on B, what is written? C, right? Then so Sultana is also going to see that, and she is going to modify it to C. Now after that, what he did, the second step he has moved to right? Then immediately what she will do is, she will, because of her extra code, then this symbol will be modified to A cap. That means what? With some 20-30 steps, we can simulate exactly what Rahim is doing. Now you see, A, B, A, C, B, A, blank. Sir, but you have A cap, right? Actually, he had only A. Yes, I understand that, but this cap is specially I designed so that this cap represents the Rahim's first tape pointer, correct? See, now this one is specially used to remember Rahim's second tape pointer, so that now next time whenever I want to do like exactly like Rahim, I can do it. That's why finally the story is like this. He will remember that, Sultana is going to remember that input heads pointers using the symbols. With various tracks, she can simulate like what Rahim is doing. So finally, whenever Rahim accepts something, whenever Rahim goes to final state, so in my notation is T, right? So since we have Rahim's code, whenever Rahim goes to T, then we also go to T. If Rahim accepts anything, we also can accept some same thing. So in that way, Sultana can say, prove that, so she is equivalent to Rahim. So finally we prove that Rahim and Sultana are two variations of Turing machine, but their expressive power is same. It is little bit difficult to understand because there are a lot of details, but try to understand the high level concept initially. Then after spending some time, apply your brain, if you really want to know exact thing. But you can understand only with 80% clarity. To understand with 100% clarity, you have to spend some time on your own and think about it, what I'm doing. Watch 2-3 times so that you can clearly understand. Okay, it's a quite complex topic, but I'm just trying here to prove that Rahim and Sultana are equivalent with some easy terms and with some of the stories, so that you can easily understand, right? But if you want to know exactly 100% with formal notations, everything, first you understand this 80%, then try to explore it. Okay, now this is about multi-tape Turing machine and multi-track Turing machine and basic Turing machine. They are all equivalent. Now we will see two-stack machine. So two-stack machine is also equivalent to your basic Turing machine, but I am not going to prove it. That's why what I do is I just explain you what is two-stack machine, what is counter machine, what is non-deterministic Turing machine, but I am not going to prove that they are going to equivalent to your basic Turing machine. Okay, so they are a little bit complicated and it is unnecessary for gate, but remember them, that two-stack machine, counter machine and non-deterministic Turing machine. Especially in counter machine, 2 counter and 4 counter, like at least 2 counter. If you have only 1 counter, remember one thing, such machine is not equivalent to your Turing machine. Okay, so apart from that, if you have 2 counter, 3 counter, 4 counter, everything, so they will be equivalent to your basic Turing machine. Okay, you remember them. Now I am going to define each and every machine, right? Now we'll see two-stack machine first. After that we'll see counter machine and non-deterministic Turing machine. Let me begin with two-stack machine definition. Two-stack machine will have, it's semi-infinite tape like ordinary Turing machine, but this is only read-only tape. That means you can only read but you can't write. but of course you can move either left or right any number of times, not a problem, like a ordinary Turing machine. The difference between Turing machines and finite automata is, so when input is given, we were able to, not only finite automata, in push down automata also input is read only, we cannot modify the input. Second thing, we were scanning from left to right, we cannot scan a symbol multiple times, correct? But here in Turing machines, so we can scan any number of times by coming left and right, okay? But the specialty of two stack machine is it is a read only tape, fine. That's why it looks like, it will have less power than Turing machine, but it is false, because we have extra support, that is stack 1 stack 2. Remember one thing, let's say you have only read only tape and you don't have extra equipment like stacks, just read only tape, then you cannot have power as this Turing machine. Definitely this read only tape machine will be less powerful than your Turing machine, but we have here stack 1 stack 2. So stack, right? This is also a stack, basic data structure stack, okay? So here you can do push and you can do pop and you can check whether stack is empty or not. Similarly here also in other stack we can do push operation, pop operation, and you can check stack empty or not, okay? Now such stacks are available with you and you have only read only tape, then using such machinery you can simulate that Turing machine. That's why Turing machine is equivalent to this I can say two stack machine. Understand? So remember it, that is enough. I am not going into details, okay? Here you can push and pop, and here also you can push and pop, and you can read the input, but you can't write. With that, so definitely we can achieve exactly like Turing machine. That's it. Now we'll come to counter machine. What is counter machine? I define, but I don't prove that why it is equivalent to your Turing machine. Just we are defining what is counter machine. So counter machine is like stack machine where you have read only tape. Here also we have read only tape. If you have read write tape, then definitely it is exactly like a Turing machine, correct? That's why we have a restriction. You have only read only tape, but you have two counters, I can say. Each counter can represent non-negative integers. Assume that, let's say you can represent integers from 0 to anything. Here also in other counter also you can maintain 0 to anything. Such counters are given and read only tape, then definitely we can simulate this two stack machine with this counter machine. But two stack machine is already equivalent to your Turing machine, right? So in that way we can prove that counter machine is also equivalent to Turing machine. So details I am not explaining, don't worry about them, you remember them. So counter machine is equivalent to Turing machine. Let me define counter machine one more time. You have a semi-infinite tape, but it is only read only. Second thing, you have two counter machines. Each counter can be incremented or decremented, and we can check whether counter is 0 or not. Similarly, you have incrementation, decrementation for second counter. Using these two counters, we can exactly simulate a Turing machine. But remember one thing, if I give only one counter, then we can't achieve the Turing machine capacity. So that is one thing you should remember. If you have more than two counters, then definitely that is equivalent to a Turing machine. Sir, if I have 100 counters, after having two counters, if you have any number of counters, then still it is equivalent to Turing machine. You can't have better performance than Turing machine. That means you can't have more expressive power than Turing machine. But if you have only one counter machine, definitely this is less powerful than Turing machine. That is enough about counter machines. Now we'll come to non-deterministic Turing machine. So what is non-deterministic Turing machine? We will see. Here you have a tape, as it is semi-infinite tape. Okay, symbols. Now the only difference between deterministic Turing machine and non-deterministic Turing machine is, so far we have studied is deterministic. So non-determinism is like this. You have a state, let's say Q, and currently I take one tape Turing machine. Similarly in non-deterministic Turing machines we can have multi-tape, multi-track, everything. First we are going to see single tape non-deterministic Turing machine. Very simple to understand. You have a state Q. On that, first we come to deterministic Turing machine. Q on A, what you do generally, you go to a next state, something Q next, and we change A to some other symbol, let's say B, and we go to left or right, correct? So this is a usual idea about transition function in basic Turing machine. But in non-deterministic Turing machine, Q on A, on particular input, we can take multiple options. That means we can change a state to Q1, otherwise Q2, otherwise Q3. In that way, any finite number of steps I can go. That means on input Q, by seeing input A, I can go to any number of states, but the number of states should be finite. Example, you can go to 50 different states. Don't worry. Then it looks like very powerful. Second thing, let me add more power. And after taking the input, by changing the state, you can go to Q1. If you go to Q1, then you can modify that A to something else like X, and then you can go to right. Otherwise Q2 and make it Y and go to left. Otherwise Q3 and make it Z and go to right. Anything in that way. So any number of decisions you can take. If I take this as action, then multiple actions are possible. In deterministic Turing machine, on particular state, on particular input, you have only one action. One state change, one tape change, that means only one symbol change, and one more thing, only left or right direction. But in non-deterministic Turing machine, what we are going to do is we are going to change our actions into multiple ways. That means we have multiple actions. Let's say each action is nothing but changing the state, changing the symbol at the current pointer and going to left or right. Such things we can do multiple. But whatever the number of choices, I can say these are all choices. So on input, your Turing machine has choices. Though you have choices, that doesn't add any effect to your Turing machine. That means still non-deterministic Turing machine is equivalent to basic Turing machine. That is sufficient. Just remember. Okay. So this is about all the variations of Turing machine.